Alright, this will be chapter 23, talking about light and geometric optics. And pretty much in this chapter we're going to continue on using light as being an electromagnetic wave. We're going to talk about some fairly simple concepts, reflection, how we can get image formation by a mirror. But we can also have mirrors that are not planar, so spherical mirrors. Then we're going to move on and talk about how light is going to slow down when it goes into different materials. So that's called refraction. And we'll kind of relate the angles using Snell's law. And we'll continue onward with total internal reflection, how fiber optics actually work. Very important concept, thin lenses and the thin lens equation. We can also have combinations of lenses. It's good to know we can form images of images. And lastly, something called the lens maker's equation, which I'm not going to necessarily hold you accountable for, but I do want you to at least know that it exists. So let's start off by talking about how we can actually visualize objects, and this is kind of saying that we have some ray model for light, and we're essentially going to say light's going to travel very often in straight lines. Now, this is an idealization, it's not entirely true, however, for all intents and purposes, it's good enough for government work. Now, what this is going to kind of mean to you is we're going to have, say, some light source, maybe the sun, maybe a lamp, something like that, that's going to shine light on this pencil. And that pencil is going to then essentially radiate light. So we're going to pick this point on the pencil, and light is going to go in all directions. Some over here, some over there, some over there, and some to my eye. You can kind of see that if I were to draw all of these various rays, it's going to be fairly complicated. So we're really only going to care about the ones that are going to go into my eye. If I had someone with their eye over here, kind of like that, then they might care about the rays that enter it. Also, kind of conceptually, you can see, have our sun right here. It's going to light up this little chunk of the pencil. Light's going to go in all directions, and I'm only going to care about the light that goes into my eye. And do pretend that is a straight line, please. Now let's start off by talking about reflection, our image formation simply by a plane mirror. This is going to be dominated by the law of reflection, which is actually quite simple. It says that the angle of reflection is going to be equal to the angle of the incidence. However, the key is this angle is going to be relative to the normal, the line that is normal to the surface. Keep in mind that normal means perpendicular. So when I go ahead and I take a look at, say, my light source right here, I've got some light ray kind of coming in like that. It's going to reflect off. The angle of incidence, the angle in, is going to be equal to the angle of reflection, so kind of that theta sub I is equal to the theta sub r is what we're going to be saying. However, this is going to be relative to the line that is perpendicular to the surface. So very important and frequently messed up concept. First thing we do is we draw a line normal to the surface, and we say that the angle in must be equal to the angle out. Keep in mind that we're not going to be talking about that angle and that angle for any of these geometric optics problems. Now, the type of reflection that we just talked about actually has a special name. It's called specular reflection, and it assumes that the surface is really smooth. So if I had a source over here, say a light bulb, and it's putting out some light rays, and they're all kind of coming in at this angle, then we're going to say the angle in is going to be equal to the angle out relative to the normal, and the light rays are going to reflect off in this direction right here. If I had an observer right here, they're going to be able to see the light. If I had an observer right there, they're not going to be able to see the light. This is going to be the type of reflection that we're going to largely be dealing with in this class. We can also have diffuse reflection, which is going to be when the surface is not rough. The law of reflection still holds. We have some light rays kind of coming in right here, and it's hitting this rough surface. For all of these, I would draw my angle or my normal angle, kind of like that, and I would say angle in is equal to angle out. The difference is an eye at these two different positions are going to see different types of light. This guy is going to see some light from this part of the image. This guy is going to see light from the top part of the image. Neither of those two eyes are going to see the full image. Again, I want you to know about this. However, we're going to be dealing largely with specular reflection. Now, what's going to happen when you look at a mirror? Let's just say, got a bottle with some cap on top. What we're going to do is we're actually going to see an image. You can kind of say, well, there's going to be some lights on in the room. It's going to be illuminating that image. and so there's light shining on that image, and the rays are going to be coming off of it in all directions. However, we only care about a couple of these. To think of this bottle, what we want to do is we want to say pick the top of the bottle, pick the bottom of the bottle, and just draw the principal rays for the top and the bottom, and know that everything in between is just going to be between the top and the bottom. So what we kind of do is we say, alright, light's going to be leaving the top of the bottle here. It's going to be approaching this plane mirror, and we draw our normal line kind of right there. We say the angle of incidence must be equal to the angle of reflection, and the light is going to enter our eye there, and kind of do the same and enter our eye there. We do the same for the bottom of the bottle. Pretty simple. However, the trick is it's for our mind to think of light bending like that. It's actually kind of unnatural. So what we actually do is we see this image that appears to be behind the mirror. So what we kind of do is kind of say our eyes are going to see in straight lines. So you can kind of trace these guys back there, trace these guys back there, and say this is going to be the image that we see. Now, a couple things to introduce is here we have the distance to the object, and here we have the distance to the image. Now, technically, this image is actually called a virtual image because the light does not actually go through it. So, go ahead and write virtual there. So, what that really says is all the light is going to be on this side of the mirror, and on this side of the mirror, there's going to be no light. Therefore, this must be a virtual image. So, sounds kind of silly, but this is actually going to be kind of a key concept for the next couple of slides. Since this is a plane mirror, we would say that the distance to the object must be equal to the distance of the image. Now, of course, we can't just leave it at plane mirrors. We need to talk about spherical mirrors, or mirrors that are bent. It turns out that we can bend these mirrors in two different ways, either concave or convex. I like to think of concave as curving inwards into the ground like a cave goes. Therefore, this one right over here is going to be a concave mirror, and then the other one must be a convex mirror. The law of reflection is still going to apply. The angle of incidence must be equal to the angle of reflection. However, if you take a look at these two surfaces, we're going to draw our normal to the surface right there and say that the angle in must be equal to the angle out, normal being this perpendicular line. The normal actually changes. So there's the surface, kind of draw our normal line here. There's the surface, draw the normal line here, and what that's going to do is that's going to bend the light rays. Law of reflection is going to apply for all these. The angle in is going to be equal to the angle out. However, the normal line is changing as we work our way across the surface. What that's really going to do is for the concave mirror, kind of see that light rays are going to bend outwards away from the center, and then for the concave mirror here, I meant convex over here, for the concave mirror, then light's going to come in and it's going to bend inwards towards the surface because my normal lines are going to be perpendicular to that line and perpendicular to that line. When it comes to spherical mirrors, just going to make a very close approximation here. You noticed in the last slide that the rays were coming in essentially parallel. For everything we're going to do in this class, we're going to say that the rays coming from a faraway object are effectively parallel. If you think of the sun kind of lighting up this tree, at that point right there acts like a source, and the rays all go in different directions, all directions really. Then if the mirror is far away, and this is going to be relative to the focal length of the lens, then we'd say that these mirrors are essentially parallel, or at least close enough for government work. Everything we're going to do in this class is going to deal with far away, so we can treat the rays coming in as essentially parallel. As you can imagine, spherical aberrations kind of annoying. It turns out, however, that if the curvature of this mirror is small, then it's going to focus the light down to a single point. So you can kind of say, hey, I've got these parallel rays coming in, do the same type of thing where draw my surface, draw the line normal to it, angle in is equal to the angle out, and each one of these rays are going to meet at some point here. This point is called the focus of a spherical mirror. It's where all the rays are going to converge. We can also say that the distance between the surface of the mirror and the focal length, or the focal point is going to be the focal length shown by this little tiny f right here. And lastly, because this is a spherical mirror, what we kind of can do is we can say it's just a chunk of a sphere. Kind of picture me, I'm completing a circle right here. And the center of the circle is going to be this point over here marked as C. If we draw a line connecting this point C and the focal length, then we have our principal axis, which really just gives us something to make all of our angles relative to. Now, pretty much as you can imagine, as we vary the radius of curvature, we're going to vary the focus. And, kind of taking a look at the diagram up here, geometry will tell you that the focal length is going to be related to the radius of curvature, simply going to be half of the radius of curvature. So if you increase the radius of curvature, you're making a larger focal length. Now let's shift gears a little bit and talk about how we can form images using spherical mirrors. We know that if we looked into, say, a shiny Christmas ornament or something like that, we're going to see our nose. To do this, we're going to do some ray tracing, and essentially there's going to be 3 rays that we're going to draw. I'll let you kind of read through them here, and I'll talk to them on the next slide. We're going to typically I tend to use just those 2. This one's a little bit more complicated, but it can be kind of useful. So on this slide we can see we have ray 1, we have ray 2, and we have ray 3. So flip back and forth between the previous slide and this one as you need to. Here we have our object. We're going to be forming images of it. It's simply a up and down arrow. And what we want to do is we want to pick one point on the object, typically its end, and say we're going to draw all the rays. So the first ray we're going to draw is going to come out parallel to the axis right here. So again, that axis is going to connect the center of curvature and the focal point. And it's going to come out parallel. It's going to go through the focus. It has to go through the focus because it's coming in parallel. It's going to kind of continue about its merry way. Then what you're going to do is you're going to, again, take the very tip of the arrow, and you're going to draw a line that goes through the focal length. So this is ray number 2. It comes in through the focal length. It must come out parallel, so kind of the opposite of ray number 1. Where these 2 rays meet, we're actually going to have the image formed. So typically you can get away with just 1 or 2. Ray 3 is kind of interesting. Essentially we're drawing a ray that's going to hit the mirror at exactly normal to it, and so it's going to go that way, and then it's going to bounce back on itself, and it's actually going to go through the center of curvature. So if you wanted to draw this one, all you would really have to do is say, I'm going to start right here, draw the ray through my center of curvature, and where these 3 rays meet, we're going to have the image formed. So this upside down arrow right here. This is not a virtual because the light is going through the image. So this is actually what we would call a real image, so the opposite of virtual. As I mentioned on the last slide, where these 3 rays are going to intersect, that's going to tell us where that point is on the object. And very typically, what we do is we say, okay, we're just going to do the tip, and once we know where the tip is right there, we can do it for, say, this slice of the arrow, we can do it for that slice of the arrow, and so on and so forth, and trace all these guys back respectively. But really, if you know where the base is, and you know where the tip is, you know that the image is going to be between the base and the tip. So we can define the magnification, that's that little m right here, to simply be the ratio of the image height to the object height. And it turns out that if you, mumble something about similar triangles, that this is going to be the negative ratio of the image distance to the object distance. So a very important equation to be able to know and use. This negative sign, what does this really mean? What it means is that the image is going to be inverted. Let's take a look. Take a look at this here. Here we have the image distance. That's the distance between the image and the surface of the mirror. Here we have the object distance. That's the distance between the object and the center of the mirror. Of course, we have our focal length too. The image distance is going to be larger than the object distance, so the ratio is going to be larger than 1. So the image is going to be larger. Also, know from ray tracing that it's going to be inverted. It's going to be upside down. So we expect HI to be less than 0. HO is going to be positive. It's above the it's above this axis right here. And so to make all the math work out, we have a negative sign right there. Keep in mind that this object is also, or this image is also going to be real because the light actually does go through it. So taking a look at this object, note that it is between the center of curvature and the focal length, and now what we're going to do is we're going to take a look and we move it inside the focal length and outside the radius of curvature. So when we move the object inside of the radius of curvature, so now we've kind of done this number right here, Yeah, we're going to draw the same principal rays. We're going to draw the ray that comes in parallel, goes through the focal point, draw the ray that goes out and comes out parallel, and we draw the funky one, number 3, that's going to go through the center of curvature. You can kind of see that rays 1, 2, and 3 never actually meet up, so they're never going to really have a focus on this side of the equation. Maybe number 3 goes through the eye, but we're not going to see a distinct image from just one ray. However, if we trace all these rays back, then you can kind of see that they're going to meet over here. Now, this is the side where there's going to be no light on, keep in mind. However, the image is going to be formed over there. It's going to therefore be a virtual image. Magnification says that it's going to be larger, and it's going to be upright or erect, so it's not going to be upside down. So what that says is the height of the image must be larger than 0. This type of mirror right here, when we bring, say, an object inside of the focal length, it's going to form a very, very large upright mirror. This is the type of mirror that you might have to apply makeup, to tweeze your eyebrows, or to shave with. And lastly, let's say what happens if we move our object outside the center of curvature. So we've looked at the object here, we've looked at the object here, and we've looked at the object over here. Essentially, the image is going to be inverted upside down. Now the object distance is going to be larger than the image distance, so it's going to be smaller, and the light goes through it, so it's going to be real. Now all of that was for concave mirrors. Let's take a look at the convex mirror. It's going to be a little bit simpler in some ways. You can think of some parallel light rays coming into a convex mirror, and what's going to happen is they're all going to be bent outwards, and we'll never be able to have an image formation on the side where there's going to be light. However, if you trace all these guys back, you can kind of see that there's going to converge at some focal point, and it's going to have some focal length. And on this side over there, there's going to be no light. So for convex mirrors, the image is always going to be virtual. It turns out that if we were to look at the objects, then the image is always going to be 1 virtual, 2 upright, and 3 smaller. Everything is still going to apply. We still have a focal length, we still have distances to the object and distances to the image, and that's just kind of the relative distance between the image in the surface and the object in the surface. Okay, some problem-solving strategies. First thing, draw the ray diagram. That's going to give you a feeling for where the image is, and give you a feeling for if your math actually works out. Then going to apply the mirror magnification equations that I've written just up here. One important thing to keep in mind, very, very, very important, is going to be sign conventions. If the object, image, or focal point is on the shiny side of the mirror, on the reflective side, then those distances are going to be positive. If they're not on the shiny side, then they're going to be negative. So coming back to this guy over here, for the convex mirror, focal length is not on the shiny side of the mirror, so in this case the focal length is going to be negative. Same thing with the image distance. It's not the shiny side, so distance to the image is going to be less than 0. Keep in mind that magnification is going to be positive if the image is upright, and negative otherwise. And then just kind of check do the math and check to make sure your solution agrees with the ray diagram.